So welcome to our series on gases, and today we're looking at Charles' law. Jacques Charles was a 19th century French inventor, scientist, mathematician and balloonist. Charles' law describes how gases tend to expand when heated. It was formulated by Joseph Louis Gay-Lussac in 1802, and he credited it to the unpublished work by Jacques. Around 1787, Charles did an experiment where he filled 5 balloons to the same volume with different types of gases. He then raised the temperature of the balloons to 80 degrees Celsius, and he noticed that they all increased in volume by the same amount. This was the experiment that was referenced by Gay-Lussac in 1802 when he published a paper on the relationship between the volume and temperature. An interesting demonstration on this relationship between volume and temperature of gases would be to take a balloon and look at its volume. So we would measure the volume of the balloon. Put that balloon then beside a hot radiator and allow the gas inside the balloon then to heat up to that temperature. What you should notice is then the volume of that balloon will expand as the temperature increases. You can take that same balloon and then put it into an ice bath. And when you measure the volume of the balloon, once the gas inside the balloon has cooled to that temperature, the volume should have decreased. You can take that balloon then and leave it to stand at room temperature, and it should go back to its original volume. So it's an interesting way to see how the change in temperature affects the change in volume. But remember, the gas must be a fixed mass and the pressure must be constant in order to see this linear relationship between volume and temperature. So in chemistry, there's a number of laws that you're going to have to memorize and equations that are associated with them. So it can often be tricky to know which equation goes with which law. So an easy way to remember Charles' law is Charles was a balloonist. He was into hot air ballooning. And when we look at balloons, we see this big volume of gas. And we often think of the little heater that's in the basket that they use to heat the balloon in order to get it to rise. So we have our volume of the balloon and we have our little heater for temperature. So that should help us remember the volume-temperature relationship for. So here we see a graph showing that relationship of volume and temperature. If we choose one volume, we can see what the corresponding temperature for that would be. If we increase that volume, we notice if we go along to our graph and down, the corresponding temperature should have increased. So to put Charles' law into words, what do we have? We have the volume of a gas is directly proportional to the absolute temperature if the pressure and the amount are held constant. So what's absolute temperature? Absolute temperature is a different scale. So you have degrees Celsius, you have Fahrenheit, you also have a Kelvin scale. Whenever you're dealing with Charles' law, you must always use the Kelvin scale. Sometimes in the questions, you'll notice that your temperature is given in degrees Celsius, and you're going to have to convert that to Kelvin. How do you do that? All you do is add a 273. So whatever Celsius value you're given, add 273 to it to get your Kelvin value. So a mathematical way to represent Charles' law would be volume is proportional to temperature. If I take a set of points on that graph that we just seen, I take a volume and the associated temperature. So the volume divided by the temperature shows that it varies by a constant amount. This is the proportionality constant, C being for Charles' law. You would have seen one similar for Boyle's law and it would have had the symbol B for Boyle, so it's C for Charles. If I take a second set of corresponding points where I have V2 and the associated temperature for that, I notice when one is divided by the other, I also get this proportionality constant Kc. So if I can say that when V1 divided by T1 is equal to Kc, if I pick another point, V2 divided by T2 is also equal to Kc, then I can say that V1 divided by T1 is equal to V2 divided by T2. Let's have a look at some word problems you might come up against when dealing with Charles' law. So if a sample of gas, oxygen in this case, occupies 500 mils at 356.2 Kelvin, what will the volume be at 293 Kelvin? So we know our equation is V1 divided by T1 is equal to V2 divided by T2. So let's find out again what our pairs are. What is our V1 T1 pair and our V2 T2 pair? So I see 500 mils at 356 Kelvin. So that would be my V1, volume in mils, and my T1, which is my temperature in Kelvin. And then I see what will the volume be, so that will be my V2 at this temperature, which is 293 Kelvin. So I just sub in my values. So I have 500 mils, my V1, divided by my T1, 356.2 Kelvin, is equal to my V2, which is my unknown, divided by 293 Kelvin. I want to transpose this equation so that I end up with V2 on its own. So I have my unknown on one side and my knowns on the other. The 293 is divided by the V2, so I will have to multiply across in order to isolate the V2. In doing so, I end up with 500 mils multiplied by now the 293 Kelvin, all divided by 356.2 Kelvin. It's always a good idea to write in your units because it will give you the units then for your final value. The Kelvin, the one on the bottom and the one on the top, will cancel each other out, leaving my unit of measure being mils, which I would expect because it's a volume that I'm looking for. When I put these numbers into my calculator, I end up with 411.29 mils. Let's check that our answer is reasonable before we move on. So I have 500 mils at 356.2 Kelvin. We know the relationship between volume and temperature is the volume increases as the temperature increases. So what happens to my temperature, the new temperature? Does it increase or decrease? It goes from 356 down to 293 Kelvin. Therefore, I would expect my volume to decrease from 500 mils to the new volume. What is our new volume? It's 411.29. So the volume has decreased as the temperature has decreased. So my answer is therefore reasonable. Let's have a look at another one. A sample of ozone gas occupies 391 mils at 298 Kelvin. The given mass of gas is cooled at a constant pressure until it occupies 87 mils. What is the new temperature? So again, what are my pairs? I have 391 mils at 298 Kelvin. They're a pair. So this will be my V1 and my T1. Then I have a second volume, 87 mils. That's my V2, and here is my T2, which I need to work out. Now this one can often be quite tricky. A lot of the time when they look at this and we fill in, so I have my V1, my T1, my V2, and my T2. Students will often move this 87 mils value to below the line, and then they will solve the equation. But when they do that, they end up solving for 1 over T2, which is not what you're looking for. You're looking to solve for T2. Now, how do I get my T2 on top? So the problem is your T2 is on the bottom. You need to get that T2 on top. A quick way to do it will be to flip both fractions. So I could have T2 divided by 87 is equal to 298 divided by 391. So you can do that. So you can invert both fractions there. To show you the long way of doing it, what we do is I multiply across by T2. So by doing that, I end up with T2 now on the top line, and it's gone from the bottom because it would have cancelled out on this side. So I end up with 391 mils multiplied by T2 divided by 298 is equal to my 87 mils. I've got my T2 now on top, which is what I wanted. I have to get rid of it off the bottom. Now I'm going to transpose, so I end up with just T2 on its own, my unknown on one side, and all my knowns on the other side. So I will move my 298, it becomes multiplied by over here, and my 391 will then become divided by. So now let's put that into our calculator. I have 87 multiplied by 298, all divided by 391. I cancel out the mils here on the bottom and the top, meaning my answer units will be Kelvin. When I do that, I find my answer is 66.31 Kelvin. Again, let's check that that is reasonable. So I can see I have 391 mils at 298 Kelvin, and I have a smaller volume when I compare it to this, so therefore I'd expect a smaller temperature. Was my answer a smaller temperature than 298? Yes, it was. So again, I know my answer is reasonable. So let's have a look at this. What is the temperature of carbon dioxide gas when it expands from 4.1 litres at 28 degrees C to 5.2 litres at a constant pressure? Now, in this instance, your temperature is given in degrees Celsius. Can't have it in degrees Celsius, it must be in the Kelvin scale. We know how to convert the Kelvin scale by just adding 273 to our Celsius value. So I end up with a Kelvin value of 301 Kelvin. Then I put in my pairs. I have my 4.1 litres and my new value, my 301 Kelvin. So it's 4.1 divided by my 301 is equal to, my V2 value is 5.2, and I'm looking for the new temperature, which is T2. Again, my T2 is on the bottom and I need to bring that to the top. You can invert both fractions to do that and then proceed as before, or you can follow this method here where I bring my T2 across by multiplying cross by T2. Now my T2 is on top and I will transpose this equation to get T2 on its own. The 301 Kelvin will become multiplied by the 5.2 litres and it will all be then divided by my 4.1 litres. The litres on the bottom and the top will cancel out, indicating that my final unit of measure will be Kelvin. When I put these numbers then into the calculator, I come out with a temperature of 381.76 Kelvin. So again, I see here at 4.1 litres, the temperature is 301. I'm now going to a greater volume, so I would expect a greater temperature. Is my answer a greater temperature than 301? Yes, it is. It's 381.76. So again, my answer is reasonable. So have a go at this one yourself. What is the new volume of helium gas that starts at 7.1 litres and 16 degrees C and is heated to 88 degrees C? So what you need to do, work out what your pairs are. 7.1 litres, 16 degrees Celsius. There's my V1 and my T1. And then it wants to know what's the new volume, that will be your V2, and you're given a temperature of 88 degrees Celsius, so that's your T2. Remember, you're going to have to change your degrees Celsius into Kelvin, and we know how to do that by adding 273 to the value of the Celsius that you're given. Have a go at those and see what answer you get. The answer is given in the next slide. So a sample of carbon monoxide occupies 3.5 litres under a pressure of 780 millimeters of mercury at 20 degrees C. At what temperature will it occupy 9 litres at the same pressure? So again, what's my V1? 3.5 litres. And what's my T1? 20 degrees C. Change this to the Kelvin scale. My V2 is 9 litres and I'm looking to find my T2. In this instance, your T2 is going to be on the bottom. You need to put your T2 on top. So you can rearrange the equations to bring T2 onto the top and then transpose for T2. So do that and see what answer you get for that, whether it's A, B, C, D, or E. And if you want to check your calculations, the answer is given on the next slide. So there's our answer there. So that's all we're going to do today, is just looking at Charles's law, and we will continue our series on gases where we'll be looking at the likes of Avogadro's law and also Gay-Lussac's law of combining volumes. But that's it for today, and thank you for listening.